Hi, I'm Kristen Grady, Marketing Director at NSR, and I'd like to introduce you to NSR's NCAT, our Non-GEO Constellations Analysis Toolkit. I will also walk you through a demonstration of how the NSR NCAT works. NCAT is an assembly of flexible and easy-to-use quantitative models that X-ray and benchmark non-GEO SATCOM constellations. Constellations, populated with thousands of satellites, are being deployed in both LEO and MEO orbits. These constellations, beaming tens of terabits per second, can transform our industry, making it vital for key decision makers to have the ability to visualize this impact at a granular level. NSR's NCAT provides this capability. NSR has developed 9 configurable tools utilizing data collected from 27 constellation shells, both granted and in-process FCC applications, in order to evaluate each HTS constellation. The NSR NCAT gives you the opportunity to add additional information from your internal database to evaluate each HTS constellation and simulate possible future modifications or other constellation initiatives. Now, let's deep dive into Tool 5 of the NSR NCAT. Tool 5 is a comprehensive resource to factually benchmark satellites and constellations' capacity at spectrum, bandwidth, and IP throughput levels. Driven by configurable inputs, the Visualization tab allows users to select 5 constellation systems for side-by-side comparison. A factual link budget analysis, which we'll review in a minute, feeds the Visualization tab. This tab provides output tables and charts with capacity metrics for selected systems. Output tables and visualizations include uplink and downlink spectrum for gateway and user beams, frequency reuse factors, bandwidth in megahertz, and clear sky IP throughput for individual satellites and beams. Tool 5 also displays the projected number of gateway and user beams, both uplink and downlink, as well as beam types, given that beams can either be fixed, steerable, or shapeable, depending on the system. Additionally, Tool 5 of NSR's NCAT calculates and displays the maximum global IP throughput capacity in forward and return directions, satellites' footprints in square kilometers, and single satellite forward and return capacity averaged per square kilometer of coverage area. Tool 5 also comes with useful maps that compare the field of view of satellites and individual beam footprints for selectable constellation shells. Given OneWeb's unique beam shapes, it's treated separately by the tool for display, so users can simply select or unselect OneWeb for comparison. As mentioned, throughput calculations are driven by a rigorous bottom-up link budget analysis for all surveyed systems, using technical characteristics extracted from FCC applications. NSR digitized all relevant technical data available in FCC filings and pasted such data in individual Excel sheets, one per surveyed constellation system. Tool 5 uses such data automatically, but NCAT users can always refer to the original documents, given that the FCC publicly shares these in PDF format. Data digitalization augments the tool's flexibility down to individual beam level and allows NSR clients to easily edit raw data and simulate system modifications, if required. The digitized FCC data feeds a factual link budget analysis, one per system. Configurable link budget analysis tabs are included for SES O3B, both current and next generation, Telesat LEO, granted, modified, and VLEO, Amazon Project Kuiper, Viasat, both MEO and the LEO modification, SpaceX's Starlink, both KUKA and future VLEOs, and, of course, OneWeb. The Link Budget tool calculates link throughput based on editable FCC data and configurable inputs like selected beams, antenna size, and other link conditions. Let's take, for example, Telesat's original Ka-band LEO filing approved by the FCC. In 2018, Telesat launched test satellites, which are orbiting at 1,000 kilometers from Earth. These satellites have been used by Telesat to space-proof its LEO system and to conduct target trials for various B2B applications, including mobility and telco backhaul, such as the announced trial with Telefonica. At this point, we do want to note that Telesat submitted a modification request to the FCC. It is included in another tool tab. For right now, we will focus on the originally planned sub-constellation with polar orbits. Telesat LEO satellites will include inter-satellite links. However, for now, let's do a single-hop link budget analysis, assuming that the gateway station and user terminal are visible by the same satellites. The tool allows the individual selection of gateway and user beams. As an example, let's say we want to calculate link throughput using the following user and gateway beams, selectable from the drop-down menus. User uplink beam number 13, which is a receiving beam from point of view of the satellite, as defined in the FCC data filing. User downlink beam, transmitting beam number 3, again from the satellite viewpoint. And gateway uplink and downlink beams number 3 and 11, respectively. As mentioned before, all blue text cells are inputs that can be modified. Let's assume the antenna size, efficiencies, and system noise temperatures listed. Since Telesat plans to include onboard processing, we need to make sure this is selected in the tool. Otherwise, it will perform calculations for a bent pipe architecture. We're assuming a single carrier for the outbound channel and a multi-carrier for the return links. But note, these are also selectable, and users can modify the power backoff for each case. Once we have verified these inputs and the buck size, we can then move down to the link budget analysis itself. The tool performs 4 duplex link budgets simultaneously, so 8 in total, assuming different combinations of gateway and terminal antenna elevation angles, as this affects path and atmospheric losses. Scenarios 3 and 4 are best and worst case scenarios with regards to link attenuation, while scenarios 1 and 2 are intermediate cases. Within the link budget table itself, users can fine-tune certain margins, such as mispointing loss, CI, roll-off factor, and network management overhead. Link budget results provide clear sky, achievable IP throughput per link and downlink beams by automatically selecting best performing modulation and coding, taken from a separate sheet in the tool with real-world modem performance data. Detailed link budget results are displayed for the mentioned 4 scenarios, providing maximum achievable beam, uplink, and downlink IP throughput, optimal modcods, and spectral efficiency in bits per hertz. NCAT's Tool 5 then shares a summary table for the link budget analysis, indicating beam and satellite throughput driven by the spectral efficiency calculated. The summary also provides sites forward and return link capacity. To the right of the summary table, it lists the bandwidth distribution of user and gateway beams based on FCC data. Note that these are also editable in case not all beams are listed in the FCC data, or if steerable beams can be used as either gateway or user beams, modifying upstream and downstream capacity and asymmetry. Last but not least, the tool provides frequency plan charts, displaying uplink and downlink frequency channels and allocations for service and telemetry links. The link budget results for each system are linked to a table called Full Table, which hosts all key output data used to benchmark systems and display comparative charts, as we've seen at the beginning of this tutorial video. As you can see, the NSR Non-GEO Constellations Analysis Toolkit is easy to use and meant for both business and technical professionals alike. NSR uses it internally to holistically assess LEO and MEO HTS constellations in support of research studies and consulting projects. Thanks for watching, and please contact NSR if you're interested in learning more about the NSR NCAT.